Hello everyone. In this video, we will be demonstrating the Gauss-Seidel Iteration Method in solving linear systems of equations. Unlike other videos in this series, we will be discussing the algorithm of this method together with the solution for the given example. This is our example written on the whiteboard. And so let's discuss the algorithm now. Our first step is to test if the set of equations are diagonally dominant, or we could also call it as the double D test. The absolute value in the diagonals should be greater than or equal to the sum of the absolute value of the rest. So the diagonal values are 5, 3, and negative 2. 5, 3, and negative 2. So let's try this one. Absolute value of 1 plus the absolute value of 2 is equal to 3. Therefore, this is greater than the sum of these two. 2 plus 8, on the other hand, is equal to 10. Therefore, this is less than the value of the sum of these two, which is, in other words, not dominant on the equation. What we could do is swap the places of these two, and therefore, maybe we could try if we could still arrive to a diagonally dominant system of equations. So let's try this one. X sub 1 plus 4x sub 2 minus 2x sub 3 is equal to negative 2. 2x sub 1 plus 3x sub 2 plus 8x sub 3 is equal to 39. So these are the diagonal values. Therefore, I'm not going to write this anymore. I think you get the idea now. 1 plus the absolute value of negative 2 is 2. So therefore, 1 plus 2 is equal to 3, which is less than the value of 4. Therefore, the 4 here is dominant. And on the third equation, we have 8. 2 plus 3 is equal to 5, which makes 8 greater than the sum of these two. Therefore, our example is diagonally dominant, and therefore, we will be able to solve using the Gauss-Seidel iteration method. So let's proceed to the second step. Find the values of x sub 1, x sub 2, and x sub 3 by rearranging the original equations. So let's do this now. What does this mean? When we say rearrange is that we will let the equation arrive to a formula that the answer is equal to the variable, or to the value of the variable rather, that we are finding. So let's try this one. So rewrite the first equation. We're going to find the x of 1, so what we're going to do is transpose and rewrite the whole equation. So x sub 1 is equal to 19 minus x sub 2 minus 2x sub 3, right? If we're going to move this on the other side, then the signs will also change, because that's a principle. Therefore, this will be our formula or equation in finding the x sub 1 across the iterations. We'll just keep on substituting the values here on the x sub 2 and x sub 3. This same goes to the x sub 2 and x sub 3. Same method. So let me just write this here on the whiteboard. As a part of the third step, or rather, not the third step yet, let's just assume the first values, or the initial values for the x sub 1, x sub 2, x sub 3. So we're going to assume that their values is equal to 1. All of them 1. So if we're going to compute for the x sub 1, 19 minus x squared minus 2x cubed, 2x, not squared though, this is x sub 2, then x sub 3, 5. Putting the values here, 1, then 2 times 1. If we solve this, we will be arriving to the answer 16 over 5. X sub 2 is equal to, I hope you have done this there by yourself, and we will arrive to the equation negative 2 minus x sub 1 plus 2 x sub 3 over 4. Changing the values of these two, or rather substituting the values 1, but we already have the value of the x sub 1 at our first iteration, therefore we will be applying it immediately on the next variable x sub 2. Solving for this equation, we will be getting the answer negative 4 over 5. X sub 3 is 39 minus 2x sub 1 minus 3x squared over 8. Substituting the values for the x sub 1 and x sub 2, we will no longer use the initial values 1, 1, and 1. We will be now using these two, 16 by 5 and negative 4 over 5. Therefore, arriving to an answer 35 over 8. So at our first iteration, we get the values 16 over 5, negative 4 over 5, 35 over 8. Let me just show you this. This is our table for the Gauss-Seidel Iteration Method. We have the columns I, that stands for iteration, x sub 1, x sub 2, x sub 3, and the percentage error of the x sub 1, x sub 2, and x sub 3 from the previous iterations. So, as you could clearly see, we don't have the values for the percentage error at the 0 iteration because we don't have a previous value of the x sub 1, x sub 2, and x sub 3. They are our initial values, or just we have just set it by ourselves. And then for the first iteration, we already have the values for the percentage error, which are great in magnitude: 69%, 225%, and 123%. So how do we solve that? We are going to use the formula rather. Percentage error is equal to the x of the present, or now, minus the x of the previous, and over the x of now times 100. So for example, the x now is equal to for the x sub 1, right? So the x sub 1, we have 16 over 5. Then the previous value of x is 1. Therefore our percentage error is equal to 16 over 5 minus 1 over 16 over 5. This is not equal, okay? This is multiplication. I'm so sorry. So times 100. So our percentage error for the x sub 1 is equal to 69%, rounded off to whole numbers without any decimal places. We're just going to need the percentage error if there is a tolerance or error bound specified on the problem that we need to satisfy. If not, we're just going to keep on using the iteration. Then if we think that it is already the roots or the solution for the set of equations, therefore I think we could substitute the values there and try if we're close to properly completing the equations. So on this table, keeping the steps that are given in the algorithm, as we go on and repeat the steps, we will be doing more iterations. And if I already done the continuous iterations on the example, and we have arrived to this table. As you could see, at the fourth iteration, we have the 2.0040, 1.0070, 4.0170 with little percentage error. As you could notice, the percentage error is decreasing. It must be decreasing as we go on getting closer to the actual roots of the set of equations. Not roots rather, but solutions for the set of equations. So I think we could safely assume that this is close to the value of 2, 1, and 4. We just think that these are the values of the x sub 1, x sub 2, and x sub 3. And substitute it, for example, at their first equation. 5 x sub 1 plus x sub 2 to x sub 3 is equal to 19. Let's try substituting this. 5 times 2 plus 1 plus 2 times 4 is equal to 19. 10 plus 1 plus 8 is equal to 19. Therefore, it satisfies the first equation. And I think it will continuously satisfy the other two equations in our set because we could predict that by looking at the table. If not, if this is not the case, though, for example, we are far from the solution, therefore, we keep on solving different iterations. I mean, continuous iterations. If we need more than 10 iterations, let's do that. But it will not be hard. It will not be difficult to do because we already know the steps. It's just continuously. Another point to remember here is this. We said that at our first iteration, we have arrived to the values 16 over 5 for the x sub 1, negative 4 over 5 for the x sub 2, and 35 over 8 for the x sub 3. On the table that displayed on the screen are all in decimal places, so these are their equivalent in decimal places. I mean in integers, or with decimal places, I guess. Up to 4 decimal places. Okay, so sorry. So here you go. 16 over 5, negative 4 over 5, 35 over 8. That's our first iteration. So at our second iteration, we will be still using, for example, the x sub 1. The solution that we have used in the first iteration. We will not be changing this. So this is the solution that we will be keep on using and then substituting the values. So the initial values for our second iteration is this, or are this rather, and then we will be substituting them here. The same goes for the x sub 2 and x sub 3. So as you could see, we already found the values for the x sub 1, x sub 2, and x sub 3. And I think at this point, we have just solved it.